Good afternoon, and thanks for joining this session today on building, fine-tuning, and deploying AI models with SageMaker HyperPod CLI and SDK. I'm Giuseppe Angelo Porcelli. I work as a solutions architect in the SageMaker AI service team. In the past few years, I've worked with multiple customers, training, fine-tuning their LLMs on HyperPod, as well as running inference at large scale. And I'm here today with Arun Nagarajan, who is a principal software engineer who has been deeply involved in the design of HyperPod and the features that we are going to discuss today. Let's walk through the agenda for the session. We're going to start with the introduction to SageMaker HyperPod, just to set the context, what is HyperPod and what are the key benefits of the product. Then we will look at the Amazon SageMaker HyperPod CLI and SDK and why we have built this CLI. Then we will get into a series of demos with live coding on getting started with HyperPod, so how you create a cluster and how you connect to a cluster. Then how do you run training of AI models? How do you do the deployment? How you optimize resource utilization using HyperPod task governance. And finally, we will also demonstrate a feature that allows you to run your IDEs and notebooks on SageMaker HyperPod. This is something that we launched a few days ago. And then we are going to share at the end some resources. So all the code that we're going to run today, you will be able to download at the end of the session. Okay. Great. Let's get started with the introduction to SageMaker HyperPod. Amazon SageMaker HyperPod is a service that allows you to manage and operate persistent clusters to train and deploy foundation models. You can scale up to thousands of accelerators, and HyperPod comes with improved efficiency. As I mentioned, HyperPod has functionalities which help you optimizing the utilization of the compute resources on the cluster. You reduce overall the time to train because HyperPod comes with advanced resiliency capabilities which help you recover from failures. When you run training or fine-tuning at large scale, failures can happen on your hardware side, on the networking side, GPU side. So HyperPod has built-in features to recover from these failures. We will talk to that shortly. Overall, the objective is for sure to lower the cost of foundation model pre-training, fine-tuning, and inference. Let's get into a bit of details of the benefits of HyperPod. HyperPod is resilient, as I mentioned. The service runs continuous health checks on the instances that are part of the cluster, and in case failures are detected, GPU failure, networking failure, the service takes appropriate remediation actions like replacing an instance or rebooting an instance, depending on the type of failure that gets detected. The service HyperPod is highly scalable. We can deploy nodes with a single spine node topology to get low latency. The nodes come with pre-configured EFA for high networking connectivity across the nodes, which we know is extremely important, especially when running collective operations. And overall, you can also implement scale in and scale out of your clusters, even automatically, thanks to managed auto-scaling support in HyperPod. It's extremely customizable. You can control the entire stack on HyperPod from the hardware side to the libraries and frameworks that you use for running your workloads. You can even SSH into the cluster nodes as needed and do whatever you need to do on the nodes. HyperPod is an efficient service, very efficient thanks to the integration with task governance capabilities, which help you allocate the computer resources across teams, defining priorities, and we're going to demo that as well. It also integrates with observability solutions like the managed Prometheus and Grafana stack on AWS. On the possibility to customize HyperPod, as you can see, you can really modify the configuration of your cluster and do customization at any layer from the hardware side with the choice of compute options, your choice of storage if you want to, train directly from S3, or maybe you want to use a high-performance distributed file system like FSx for Lustre. You can choose the framework of choice, PyTorch, TensorFlow, JAX, whatever you prefer. And you can even connect to your preferred experiment tracking solution. We offer managed ML flow on AWS, but if you want to use, for example, third-party solutions like weights and biases, you can definitely do that. You have full flexibility. What is important to note is that you have a choice of 2 orchestration options on HyperPod. On one side, you can use Slurm, for those who prefer the Slurm experience. On the other side, you can integrate, so HyperPod automatically integrates with Amazon EKS to provide Kubernetes-based orchestration for your nodes. And that's indeed the focus of this session, so we are gonna focus on EKS orchestrated clusters for which we have built the HyperPod CLI and SDK. At high level, the architecture for HyperPod EKS orchestrated cluster looks like what you see here on the slides. On the right-hand side, you see the HyperPod managed nodes, so the service takes care of managing the compute nodes. Then once you deploy a HyperPod EKS cluster, you are also going to create an EKS cluster in your account, which acts as the orchestrator for the HyperPod managed nodes. And then users will use the Kubernetes APIs provided by this cluster to interact. The interaction can happen from any client. You can use SageMaker Studio, or you can even use your own terminal on your own machine, which is what we're going to do today. And for administrators, on the other side, you can still use Kubernetes APIs to configure the cluster, set up the cluster, as well as I already mentioned, you can establish AWS Systems Manager, Session Manager, secure connections to cluster nodes so that you can kind of SSH into the nodes and configure the nodes as needed. On the storage side, the storage will be for sure configured in your accounts because that's where your data resides. And you can use S3, you can use FSX for Lustre, or as I already mentioned, you can connect to any file system that might be running in your account. When the HyperPod cluster gets deployed, elastic network interfaces are created in your account, in your VPC, and then from that VPC, you can connect to your own solutions for storage as needed. Great. Let's move on to the HyperPod CLI and SDK and why we have built another, I would say, CLI and SDK. Why another is because to integrate with, so to work with the Kubernetes cluster, I'm pretty sure you're familiar, you can use kubectl, the Kubernetes CLI, and just run commands there. But the feedback that we have received from our customers, from data scientists and researchers, is that using kubectl is definitely fine, but it's very complex. You have to manage YAML configuration files. You have to edit those files and then submit the workloads. And while this is could be extremely easy for those who are familiar with this process, sometimes data scientists were looking for a more abstracted interface, which is also closer to the type of workload that they are running, which is indeed a GenAI workload. It's not like a generic deployment of Kubernetes resources on the cluster. In addition to that, some users prefer a more kind of a programmatic interface with an SDK-based interface. Others prefer command line interface, so that's why we have built this new solution which brings together CLI and SDK. And for sure, to also leverage better leverage the observability capabilities that are available on HyperPod. The HyperPod CLI and SDK is an open source project which is available on GitHub, on the SageMaker HyperPod CLI repository. You can see an example of running the hype command and see the help that guides you towards the actions that can be executed with the CLI. On the architecture side, I hope this is readable. The way it's structured, what is important to get from this slide is that it's a layered architecture. On the top layer, you see the user experience layer, which is either the hype command for running commands with the CLI, or the import SageMaker HyperPod, essentially to work, the HyperPod package to work with the SDK. And then you find the core modules of the CLI and the SDK. Core modules of the CLI implements the actual CLI commands. The modules of the SDK are the ones who are responsible to build the requests that then will be submitted to the Kubernetes client. It's important to see how we are reusing the SDK modules for the CLI commands. So the CLI has been built on top, I would say, of the SDK itself. So it uses the SDK to execute the commands. The SDK, as I mentioned, uses Kubernetes client to then run the commands against the Kubernetes APIs. And on the right-hand side in pink, you see the templates. The templates are the representation in the CLI of the custom resource definitions that are defined by the various operators that are installed in the cluster. So these templates are versioned so that in case the operator gets updated on our side, you can still continue to use the CLI with the previous version of the operator. So you don't necessarily need to upgrade to the latest version. How to get started? Sure, create your HyperPod cluster. On the cluster creation experience, as you can imagine, setting up such sophisticated environment requires, to look at networking, to look at the storage layer, security, as well as, the actual compute. And in order to simplify this process, we have recently launched simplified cluster creation experience from the AWS console. This cluster creation experience allows you to use quick setup, which comes with opinionated kind of defaults on the infrastructure side, how to set up your VPC, how to configure the CIDR ranges for your cluster so that depending on the scale of your cluster, you are sure that you have enough IPs available for your machines. All these things are pre-configured there. You can just easily spin up your cluster. But if you want to tune the configuration, you can move to the custom setup. And then in the custom setup, you can decide what to enable or what to change on the configuration of the cluster. For example, if you don't want certain operators to be installed by default, or if you want to change networking config storage and so on. Great. And then for installing the CLI and SDK, you can just run pip install SageMaker HyperPod in your environment. Great. Let me move to the code, and here we go. So before we get into the actual examples, I just want to show you the cluster that we are going to use today. So I am in the SageMaker AI console, and then I can move to the HyperPod clusters. And I have 3 clusters running here. 2 are EKS orchestrated, and 1 is Slurm orchestrated. And we're going to use this cluster, ML cluster AIM371. And here from the console screen, you can also see the corresponding EKS cluster, which is acting as orchestrator for the HyperPod nodes. And then you can find here all the configuration, including the observability configuration, so which metrics we decided to export to Prometheus and Grafana from the cluster. And what is important to look at is also the configuration of the instance groups. So here we have 2 instance groups, one with G5 12XL instances, which come with 4 A10 GPUs on board for each instance. And then we have a few compute CPU nodes as well in the cluster. All the nodes, as you can see here, are running from the details. So 4 G5 12XL and 6 T3 2XL instances. Great. Now, let me move to VS Code, and the code that I'm going to show right now, you will be able to download later. It's a modular example. It starts from getting started, then goes into training, inference, task governance examples, and then spaces, so running IDEs on HyperPod. Let's start from the getting started. In the first module, you will see how to set up the cluster and all the things that we have discussed so far. I don't want to spend too much time on this, how to install the CLI, but then we can just check. I am in this directory where I've created a virtual environment where I've installed the HyperPod CLI. Indeed, if I run the hype command, I should see as output the help essentially on the CLI. Great. I can also do something like hype -- version to check the version of the CLI that is installed, and as I mentioned, the versioning of the templates that are available with the CLI. Great. Let's take a look at the various clusters that I have in my account. So the list cluster operation will list the EKS orchestrated clusters that are available in my account, and as you can see, we have the AIM371, and then we have also the ML cluster EKS, the other one that I have. Great. Now, what you need to do to start working with this cluster is setting the cluster context, so essentially updating the local kube configuration so that you can execute API calls against the Kubernetes API correctly. So When I run this command, you will see that it will update the local kubectl. And yeah, so we are ready to run commands. And if you want to see, what is, sorry about that. So if you want to see what is the current cluster context, you will just run the get cluster context, and you know exactly which cluster you are working with. Great. We have pre-installed all the required operators and add-ons on the cluster, so we will skip these steps, like setting up the training operator, setting up task governance, and so on. What I just want to mention is that this cluster has an FSX file system attached, where data and the training code is stored, just for your reference for the future examples on training. And this cluster has been set up with, so the FSX has been set up with the data repository association, so it's a kind of a sync between the FSX file system and an S3 bucket, so that whatever you write in S3 gets made available in the FSX file system and vice versa. It's a bidirectional sync. Great. Now, once we have seen the initial setup, let me go into the steps to create HyperPod cluster using the CLI. First thing that we can do is we can run this command to create just a directory, working directory for the create cluster operation. I can run the hype-init cluster stack command. The hype-init operation is going to create in your local directory two files, one config.yaml and the other one is a Jinja template for the CloudFormation template parameters. As I mentioned, the HyperPod cluster creation experience is based on CloudFormation behind the scenes. So when you create a cluster, whether it's on the AWS console or through the CLI, we are deploying CloudFormation templates in your account. Now, and this is consistent, so whatever you use as interface, either UI or the CLI, you get the same experience. So what the CLI is doing here is downloading the values that need to be provided to the CloudFormation template for deployment. And these are templatized in that Jinja template. Jinja is a framework for a templating framework, essentially. And we can look at these parameters here. It's very kind of complex set of parameters which go through, the configuration of the availability zone, if you need a NAT gateway in your VPC, the instances that you want to deploy, the instance groups that you want to deploy, the file system configuration, how to deploy FSX in which availability zone, through which subnet, and so on. Great. On the other side, you have the config.yaml. The config.yaml is a way more abstracted configuration file, which gives you just almost the same knobs that you find in the console, you have available in the config.yaml here. So you can change, for example, the Kubernetes version that you want to use on your cluster, or maybe you can change the operators that are installed on the cluster. You can decide to change the configuration of the instance groups. For example, in this example, we are just deploying a single T3 medium. So there is one T3 medium instance count is 1, and the instance type is T3 medium. So it's just one instance in one instance group in the cluster, and so forth. You can set the VPC config and so on. From the CLI side, you have two options. Either you edit this config.yaml through your editor, so your preferred editor, or you can use a command which is called configure, this one, to automatically edit that file, the config file. So for example, here we are updating the Kubernetes version to 1.33. So you can see that has been updated. And after you do that, you can just do hype validate to validate that your configuration does not contain errors. And finally, you can do hype create, which will trigger the cluster creation. So one thing to note is that in the run directory that gets created here, we'll also find the evaluated CloudFormation parameters. So the template in which the parameters the placeholders, have been replaced with the actual parameters for your reference. This is useful, for example, if you don't remember how you had configured the cluster, some sort of light experiment tracking solution available on your file system when working with the CLI. Great. If we go back to the cluster screen, we will see that we have indeed a new cluster being created. It's here, HyperPod cluster stack here. And the creation is in progress. You can monitor the progress going to CloudFormation. And you will see that there are here a few templates, a few stacks being deployed. This is the main stack, HyperPod cluster stack, which then has a number of nested stacks for the various components that need to be deployed, VPC and so on. Great, this concludes the demo for the cluster creation. We'll not wait for the cluster creation because this takes some time. Let me move on to the next topic, which is about training.
All right, thanks, Giuseppe. HyperPod ships with the training operator, which is a sophisticated end-to-end training system, which is built from the ground up for AWS. I wanted to highlight a few key features that the training operator supports. The first one being the super fast failure recovery. In the traditional training systems, when a failure happens, usually the containers and the images are torn down so that all the initialization work is lost. With the HyperPod training operator, it's a lot more smarter in that it is not going to tear down the container when a failure happens. What this means is that when a GPU fault happens or a network issue happens, your training job is not stuck on initialization for too long. What used to take minutes will take a few seconds. Secondly, the operator supports something called custom monitoring. What we mean by that is that in addition to monitoring for the infrastructure failures, including the GPU issues and network issues, the operator can be configured to monitor the failures happening in your training job logs. For example, you may have encountered issues where the job is stuck, it's not making any progress, or you are coming across a sudden spike in the loss curve, or you have other issues which are preventing the training job from progressing. The operator comes with ability for you to specify what you want to monitor, and you only need to set up the config and the operator watches your back. And thirdly, the operator also integrates with the task governance system, which we will talk about a little bit later, and that will help maximize the utilization of the precious GPU resources. Okay, so with that background, let's jump into seeing how this comes alive in code. All right, so what we see here is a training data set, and we are going to train a model not just for text completion but also for reading the query from the user and then deciding what sort of tools it needs to invoke and then read out loud the thought process which the model went through. This training data set is a little bit hard to read, so I pulled up one particular example. You can see that there is a system prompt, and then we are introducing the available tools to the agent, and we have a user prompt, and the assistant decided to invoke a particular tool, and then here is a tool response, and based on this tool response, the assistant knows to read the various fields it asked for and construct a user-facing message and then sends it to the user. And then the user asks follow-up question, and this multi-turn events keep going on. So that's one example. And for today's demo, we are going to use this data set and train a Qwen 3 model. Giuseppe showed you how easy it is to create a cluster at the infrastructure level with a single command. But what about the distributed training side? You do need to understand what sort of framework you're going to use, how are you going to get that image in your cluster, and then perhaps understand how do you submit or run a job with Kubernetes. The HyperPod operator simplifies all of that into a single command. I have previously uploaded the training data set to S3, and let me quickly check if we still have the data set. Okay. So we have the training data set and validation data set. That's the same one I showed you earlier. I will also check the ECR image. So we have the ECR image set up here. Now I'm going to submit this job with this command create job, and that's it. Once we submit this job, what the CLI is doing is that it is constructing the right Kubernetes spec file and submitting it to the cluster. You can see that we asked for 2 nodes of G5 instance type and 4 tasks for training processes per node. And we pointed, okay, here's how you get your data and so on. Now let's check what happened to this job by listing all the jobs in this cluster. You can see that the job that we submitted is already running. Great. Let's get some more details about this job. You can see that this job asked for 2 replicas, 2 pods are running, and then 4 processes per node, and it was created, pod started running, and the training job itself is running. Now the next level of detail is that if you want to look at the pods themselves, we can do the list pods, which should tell you the 2 pods that we asked for. Now we can look into the pod logs, which is basically your training job logs, and see what is going on there. We can see that initialization completed, and then the checkpoint is loaded, and the training is starting. So to recap, what this operator did was that with a single command we specified the training image and the configuration that you wanted, and the operator kicked off the various training parts that are necessary to run on Kubernetes, and it's doing a lot of heavy lifting wherein it is asking the parts, are you doing okay, with the health messages, all these health messages that you are seeing, or the health checks happening from the operator side, reaching out into each pod asking if they are doing fine. And if any of the nodes are not doing well, then the system will help repair that. Speaking of fault resilience, let's say we want to observe what happens when a fault is noticed. In production, the HyperPod nodes come with the health agents, which will automatically identify if there is a fault that is happening and flag the nodes for replacement. But for this demo, I'm going to manually do that, and let's see all the parts that are running, and these 2 are the parts that we just now kicked off through the training job, and I'm going to mark this node as a failing node. I'm going to apply a Kubernetes label which will mark this node as failed and pending reboot. To repeat, usually this is taken care of automatically by the system, but just for demo I am just labeling it so that we can observe how the operator deals with it. Now let's check what happens to the pods. Remember we flagged this node which is ending in 917. Now you can see that the same pod, it got scheduled to a different node and it's already in running status. Let's describe the job itself to see what status it recorded. When we do that, we can see that the operator observed the node fault that happened outside of its control, and it remediated it within 6.5 seconds. That is the key heavy lifting that the operator offers, where you don't have to worry about the faults happening in the system, and you don't have to wake up at 3 a.m. to fix some training job which is going to fail because one random GPU decided to quit. Okay, so let's quickly take a look at the other initialization way for submitting the job, which Giuseppe also showed, but in this case it's for the training. This is a common pattern across all of our operators, where you create a directory and then you call init on the particular type that you want to work on, and the CLI creates these templated files for you. If we open up here, you can see that it has a few details all blank, but you can go ahead and fill them either with the configure commands, or you can edit directly with your editor. Now, if we quickly check this config file, the two fields that I specified, job name and image, are already filled in, and I can do validate, and then I can do create to submit the job, which I'm not going to do right now. All right, so up until now we have been talking about the CLI abstraction. I also wanted to show the SDK abstraction. Here what you see is that in addition to the CLI interfaces, we also have the Pythonic SDK implementation for all of our interfaces. For example, you can import with the standard Python behavior. You can either use Notebook, or if you have automation that you want to build on top of this, you can write standard Python code for this. Here is the HyperPod PyTorch job class that you can instantiate and provide all the different configurations that we talked about. And then finally you can call create on it to simply submit a job. And you can do the list operation, the status operations, pod log operations, all of the capabilities that we looked at earlier, they are also available through the SDK interface as well. Okay, so that concludes the demo for the training operator. Now, before we jump into the inference operator, I just wanted to recap how quick and simple it was to use the HyperPod CLI or SDK to submit a training job, and you didn't have to worry about fault recovery, and the fault recovery is really quick. And to recall the layer diagram which Giuseppe shared, this is all a layer on top of Kubernetes, kubectl for example, right? And if you want, you can always drop into the Kubernetes level commands. For example, if you want to get the parts, that's still there for you. If you are an advanced user and if you want to use kubectl, that's all good. But if you want to have an abstraction with which you can build on top, we have the CLI and SDK for you. Okay, so let's move on to the inference operator. I have a slide to show you what features it has, but I want to kind of kick off one creation of the endpoint because it takes a few minutes. Hopefully we will have time to see that in completion. So I'm going to delete the job that we created. And make sure that that job is deleted. Okay, so we don't have that job anymore. Now we are ready to kick off the inference deployment. This one I am going to use the config way, and I already have the config bootstrapped. So I'm just going to say validate and create. So that's going to kick off the creation. Okay, so that's going to take a few minutes, and we will come back to it in a moment. All right. Now, HyperPod ships with a inference operator, which is how we are going to deploy and scale your AI models. I wanted to highlight a few key features the inference operator provides. The first is the simplified deployment. HyperPod operator not only deploys custom models that are trained by you or from the predefined models from Jumpstart in SageMaker, but also it creates all the infrastructure required for a production scale inference endpoint. For example, you need to set up the ALB to expose it to an application, and then you need to deal with the SSL certificates and termination, and then you need to deal with auto scaling policy. All of that is taken care of by the inference operator with one single command. Secondly, like I hinted, whether your model is in FSX or S3, which you have trained, or if you want to use the built-in models from SageMaker, those options still exist for you to choose whatever you want to deploy. Third is the auto-scaling support, where the inference operator is integrated with the metrics from CloudWatch or Prometheus, and it watches for scaling events, and then it scales automatically for you. This operator works seamlessly with the Carpenter auto scaling with HyperPod, and then provisions the instances as they are needed. And finally, the idea is that for different audiences, you can go through different flows. For example, the data scientists and ML engineers, they can use the HyperPod CLI and SDK, which we will demo in a bit, to create the endpoints, and which in turn creates the SageMaker endpoint, the ALB controller, CADA, and then integration with FSX, S3, and metrics. All that stuff is taken care of you with a single command. And when all of this is set up and ready, the application developers can interface with the ALB directly or through SageMaker endpoints to do actually invocations on the model themselves. With that, let's switch over to the demo. Okay, I know I rushed through the creation of the endpoint, but let's take a quick step back. What we did was that we are going to deploy a custom model, and I'm going to show you that the model exists in the S3 bucket, which it is deploying from. You can see that this is the model that we are deploying currently. And what I did was the config way of deploying, and you can also see that the equivalent CLI way of deploying is also available for you, where you can specify the endpoint name, where is your model. For example, this one we took it from S3, and what's the bucket name, where is the model located, instance type, and then the image URI. Notice that this image is directly from SageMaker, from the DJL container. And once the endpoint is ready, we will be able to do inference against it. But let's check what is going on with the endpoint that we created a few minutes ago. I'm going to list all the endpoints in this cluster. Okay, so it says deployment complete, which means that the pods should be in a running state. We can also take a look at the internal operator logs for the inference operator itself. You can see the metrics are enabled, the inference endpoint config is all being set up. And then we can also take a look at the detailed logs from the custom endpoint CRD. Okay, probably I made a typo. Okay, so what we see here is that the deployment on the pods have successfully completed, but the front end endpoint, the SageMaker endpoint, is still under creation. While we wait for that, we can perhaps look at some of the pods. Okay, so we have a pod which is ready to do inference, and we can look at the pod logs. You will see that the initialization completed, it would have loaded the model, and you see this, it has loaded the model, and then it has started the worker thread, and the endpoint is ready from the pod. We just need to wait till the SageMaker endpoint is complete before we can do an inference. Okay, there we go. The SageMaker endpoint is also created. We can do a quick invocation on this. Okay, there we go. The chat completion came along, and the inference endpoint is up. All right, so that concludes the demo for inference. We have another way to do inference deployment, which probably we don't have time to do it, but the idea is that just like we did inference deployment from S3, you can do something from SageMaker's Jumpstart as well, where you only need to specify the model ID, and automatically it knows to download all the model and everything and deploy this for you. So to recap, what we saw is that with a single command, the system takes care of the heavy lifting required to setting up the load balancer, the auto-scaling controllers, the metrics, the logs, and kicking off the deployment for Kubernetes. All of that is taken care of you out of the box. We do have some examples here on invoking or forcing an auto-scaling event, but we will skip that for the time. So the next part of the demo would be handled by Giuseppe again. Yeah.
Switch. Yeah. Can you delete it? Great. So as we mentioned earlier in the talk, so HyperPod provides capabilities, built-in capabilities to optimize compute utilization on the cluster. This is thanks to HyperPod Task Governance. HyperPod Task Governance gives you the possibility to define a policy at the cluster level and define multiple priorities for workloads. In this example, you can see how, for example, the inference priority is higher than maybe experimentation or training priority. This allows your workloads to be treated differently, and higher priority workloads can be configured to preempt lower priority workloads. At the same time, you can decide how to allocate the compute resources that you have available in the cluster to the various teams. So a team corresponds to a Kubernetes namespace, and what you do is you say, hey, team A has allocated a certain number of instances. Well, the compute resources of an instance, like, I don't know, X GPUs, memory, as well as CPU resources, or you can go even granular. So just a certain number of GPUs or a certain quantity of memory, certain number of vCPUs. Both options, so entire resources of an instance, as well as granular resources are available. Thanks to this setup, you can also configure how to borrow and lend compute capacity. So you can say that team A, for example, can borrow 100% of their compute capacity if there is idle compute capacity in the cluster. So this means that if team B, for example, is not utilizing the compute resources in the cluster, which are sitting idle, team A could borrow these compute resources while those are idle. When team B comes back with guaranteed compute requests, so the quota that has been guaranteed to team B, then the team A job will be preempted. And that's what we are going to demonstrate right now. Let me move back to the code. Yeah, so we are in the task governance section of the examples. Let me set up some variables. We're going to use the same training job that was run earlier, but we're going to configure in a different way to assign different priorities and running the job by different teams. If we quickly go back to the cluster, we can see that the cluster has been configured. On the policies side, you can see that I have the priority classes that you have seen, almost the same that you have seen on the screen here, configured on the cluster. And then we have the compute allocations. If we go to the compute allocation for a specific team, we will see that team B has just one instance that has been allocated to the team. So one G5 12XL, so 4 GPUs are allocated to this team. They can borrow 100% of the compute. And the team A is configured in the same way. So they have one instance guaranteed compute for this team, and they can borrow 100% of their compute resource. So another instance, the compute resources of another instance, essentially. Great, let's go back to the code. Now we can show an example. As you can see, the command is almost the same. What we are setting here is we are defining the namespace that we want to run this workload in, which corresponds to the team that the compute resources have been allocated to. The local queue, task governance integrates with queue, which is a popular scheduler for Kubernetes, just offers a layer to configure queue in the appropriate way. And then we are setting the training priority for this job. Okay, so and the instances that we are requesting are 2, okay? Let me run this code. Oh, sorry. Let me run this job. Okay. Let me check if I copied everything. Indeed, I was wrong. Okay. Great. Okay. The job is running. Now we can run this list command to see that the job has been running. And as you might have noticed, we have run this job with 2 instances, but this team A, had just one instance allocated. So this means that we are borrowing the idle compute from team B at this point. Let's check if that is the case. We can run this command on the queue side. So first of all, we can also describe the job details as needed to see if the job is running correctly. Okay, indeed, it's running. And we can then run this kubectl command, which will look into the cluster queue, the queue cluster queue. And you can see that we are borrowing 4 GPUs. So since, as I mentioned, this team has access to one more instance, and this instance has 4 GPUs on board, now we are borrowing 4 GPUs with this job. Great. Okay, let me simulate now a scenario where the team B wants to submit a job with just one node. Okay, so their guaranteed compute. This is their guaranteed quote. Okay, so let's run this task. Okay, so now we should see what would you expect to see is that the team A job is in suspended state because it was preempted, and the team B job has been created and it's indeed running. Another thing that we can do is we can preempt a lower priority task. So within team B, now a higher priority task kicks in, so which has the experimentation priority, which is higher than the training priority. So now what we expect there is that this task will take higher priority on the cluster, and the other one will be suspended. Let's take a look. Okay, so we have team A suspended, team B, one job is suspended. The one which was triggered with a higher priority has now been executed. And now what we can do is we can also, delete, for example, the job with the higher priority. This is the one with the higher priority that we just submitted, and we should see that the team B job now gets restarted. So the team A is suspended versus team B's one will be reactivated, okay, resumed. Then we can delete, for example, the job from team B. So at this point, my expectation is that we will also see, we are deleting this job, and we will also see, oh, sorry, what happened? Let me double check. Okay, it's called QQuent Team B, I guess. Is the name correct? Yeah, seems correct. Let me double check. Okay, maybe a typo. And then now we can check the jobs, and we expect the team B's jobs for sure have been all deleted, and the team A job has been resumed. So it's borrowing again the idle compute and has been resumed. Okay. So now we can just delete the job to clean up the current status. Great. The last thing that I would like to show you is how to manage now IDEs on HyperPod clusters and how to run IDEs on HyperPod clusters. Great. We recently launched this capability, which allows you to execute your IDEs, whether SageMaker Code Editor, which is based on CodeOSS, Visual Studio Code open source, or JupyterLab on the HyperPod cluster. The idea is that once you have a cluster up and running, and this cluster is being utilized for training or inference, you might also want to run your IDEs, your interactive ML, let's say workloads, reusing some of the compute that might be available on your cluster at a certain time. You also get very fast startup latencies because you can pre-cache, the container images for your IDEs on the cluster, so the environments are bootstrapped very, with a very short latency. And in addition to that, you can for sure reuse the same tooling like the HyperPod CLI to work with the IDEs. The IDEs on HyperPod is integrated with task governance capabilities, the same capabilities that we have seen right now. So this means that, for example, you can, have your IDEs running with a certain priority, but then if a higher priority workload is kicked in, you might decide to preempt those tasks because you might want to use the GPUs for some other task. But at the same time, your users can take one GPU, for example, from one node and work on their notebook or with their VS Code, using this GPU. as well as even a fraction of a GPU, because we have added support for fractional GPUs using NVIDIA MIG technology, so partitioning the GPUs into smaller fractions. Great. I'm not going to spend too much time on the details of this capability, but you can create multiple templates as well for your IDEs, so that each template defines the image that you want to use, some configurations on the instance type, default instance type, the default computer resources that are going to be requested, so that the users, when they spin up the environment, they can just use the template. They don't have to provide all the parameters like, I need these computer resources and so on. So the administrators can set up various templates that are then utilized by the users to spin up their environments. Okay, let me move to a demo for this as well. Okay, need to switch back. Here we go. Great, let me open the last module, which is the spaces one. Okay, so let's set a variable, which is, the name that we want to give to the space. And then as you can see, we are running here this command, the create space, with a node selector, which allows us to create this environment, this IDE environment, on a CPU instance. We don't want to use GPU instances for this task. We can use a simple CPU instance to spin up the environment in this example. And we're also mounting the FSX file system. Okay? So then we can use still the CLI to run commands like list of the spaces. I have two running. Actually, I've pre-created one space on my side, and then this is the one that is being created right now. Yeah, we can also run a describe operation to see the details on the space. What I want, so this is all the setup about the space workspace is starting at this point. Okay, great. What I want to show you now is how to access these spaces. There are two options here. One is to use the remote connection via VS Code, so you can set up a remote connection. So you have your pod running on the cluster, but then from your local VS Code, you establish a remote connection. So you use the remote compute for your workload from your local VS Code, and that's one option. And in order to do that, let me take the name of the space that I have already running on my side, which is called this one. It's my Jupyter Lab space. So space name equals my Jupyter Lab space. And then you can use this command, which is called create hype space access with connection type set to VS Code remote. And this will give you a secure connection URL to the remote space. Once I run this URL, let's say I run it on my browser, this will automatically open VS Code. I can open it, and what you can see is that now VS Code will establish a remote connection to the space, okay? So now I'm running on the remote space. Just to take a look at this, I can do new terminal, do ls. This is the home directory on the space, but I can also do FSX, so I'm connecting to. So this is the distributed file system, the FSX file system that I have attached to my cluster, that I've mounted to the space as well, so that you can do things like look at the checkpoints. This is the previous example on training that we were running. Okay, and here are the checkpoints, the model artifacts, the scripts that we were executing, and so on. This is one way to work with the space. The other way is via the web UI, and you can just run this command to get a web UI URL, and we will see that just clicking on this link, I can open this website, and now we are connecting to the remote space via the web UI. This was Jupyter Lab space, and we're now connecting to the Jupyter Lab service here. Yeah, that concludes the spaces demo, and actually concludes the session for today. And here you can find all the resources regarding the functionalities that we have covered today. What is important is the, oh, sorry. Sorry. Yeah, here we go. So what is important is the QR code that you see there, from where you can download all the examples that we have gone through today, even more, with more examples. I'll leave this for a minute or so, and then move to the next slide. And then we can stay here around in case you have any questions, since I see that we are right on time. So thank you.
Thank you.